Hello, AP Stat students. Previously, we've talked about sample proportions using categorical data. Now we are going to talk about sample means with quantitative data. When we record quantitative variables, we are interested in other statistics, such as the mean, median, and standard deviation. Sample means are among the most common statistics. Let's take a look at the mean household earnings for samples of size 100. But on the left, we have the population distribution. And on the right, we have the sampling distribution. What do we notice about the shape, center, and spread of each? And that is this question that we're going to answer. And if you look at the population distribution, it is definitely right skewed. As far as the center has a mean of about 80,000 right here. And the range, from what I can see, is, I want to say, from 0 to about 250,000. So that's our spread. Even though there's a large spread, I don't really see any obvious outliers, so I'm going to leave it at that. As far as the sampling distribution goes, this is of samples of size n equals 100, so sizes of 100 are taken from the population distribution, and then their means are graphed, and the result is that sampling distribution. As you can tell, this is more symmetrical looking, so I will put that information down here, I guess. The mean of this sampling distribution, so let's use the correct notation, the mean of the sample is the same, so it's 80,000. And the range is, I'm going to say 50 to 100,000, so 50,000. That is our spread. And so what is this telling us? Well, when we choose many simple random samples from a population, the sampling distribution of the sample mean is centered at the population mean mu. So this center, so the mean of the population or of the sampling distribution is equal to the mean of the population. And it's less spread out than the population distribution. So the sampling distribution, when it's less spread out, then the standard deviation, and these formulas are on your formula sheet, of the sampling distribution is equal to the original standard deviation of the population divided by the square root of the sample size. And therefore, this is a smaller spread right here than the population distribution. So we can write that information here as well. The mean of the sampling distribution of X bar is equal to the mean of the population. And this is for a simple random sample of size n drawn from a large population. And the standard deviation of the sampling distribution is equal to the standard deviation divided by the square root of n. Now, you can only use this formula for the standard deviation as long as you're sampling with replacement, or if you're not sampling with replacement, as long as the 10% condition, which we learned in the previous section, is satisfied. But here's a little note. These facts about mean and standard deviation of X bar are true no matter the shape of the population distribution. Let's do an example. Okay, suppose that the number of movies viewed by students in the last year by high school students has an average of 19.3 with a standard deviation of 15.8. Suppose we take a simple random sample of size 100 high school students and calculate the mean number of movies viewed by the members of the sample. What is the mean of the sampling distribution? So the mean of the sampling distribution is equal to the mean of the population, and therefore that is equal to 19.3. What is the standard deviation of the sampling distribution? Check whether the 10% condition is satisfied. So let's check the 10% condition. Our sample size is 100. Multiply that by 10. It is reasonable to assume that there are more than 1,000 high school students. And we don't just put reasonable to assume. Make sure you write it in terms of context. Okay, so now that we know that the 10% condition is satisfied, we can calculate the standard deviation of the sampling distribution, which is equal to the standard deviation of the population divided by the square root of n, and that would be 15.8 divided by the square root of 100. At least this is easy calculation here. So you have 15.8 divided by 10, and that is just 1.58. Right. Now, another important idea to note is, before we do the next example, the sampling distribution of a sample mean if it's from a normal population. Suppose that a population is normally distributed with mean mu and standard deviation sigma. Then the sampling distribution has the normal distribution as well. So if the population distribution is normal, the standard deviation or the sampling distribution will be normal. With the mean and a standard deviation of sigma over square root of n, provided that the 10% condition is met. So that still has to hold true. This is true no matter what the sample size is. So this is really nice. Let's do a couple of examples. The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal, with a mean of 266 days and a standard deviation of 16 days. On number 1, find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. Okay, so we can use a normal CDF because we know the population distribution is normal. So normal CDF, for some of you who don't label your numbers in here, you need to do that, especially when you're doing your test. So our lower bound is 270. Our upper bound, you just want to make it something big because the standard deviation is 16. So you want to at least make it big enough that it's 3 standard deviations away. So you could do something like 400 or 500. I just picked 1,000. Our mean is 266 days. And our standard deviation is 16. And why did I choose 16 instead of using the formula? Because this is not a sample. This is from the population distribution. And so plugging it in, doing our second vars to get normal CDF, I get 0.4013 as my probability. Now, in problem number 2, we have a simple random sample. So here's where our sampling distribution will come in of 6 pregnant women. Let X bar be the mean pregnancy length for that particular sample. What is the mean of the sampling distribution of X bar? So the mean of the sampling distribution is equal to the mean of the population, which is 266 days. On number 3, what is the standard deviation of the sampling distribution? Is the 10% condition met? Well, it's definitely reasonable to assume that there are more than 60 pregnant women. Right, so now that we know that the 10% condition is met, we can calculate the standard deviation of our sampling distribution, which is equal to the original standard deviation divided by the square root of n, and our sample size is 6. And that ends up being 6.53197267. Again, I'm using all these extra digits to minimize rounding error. Find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. So again, the question is very similar to number 1, but this time it's asking us in the sample. So you got to really be careful when you're reading these questions. So if you're putting in the right standard deviation. So we will use our normal CDF. And we have the lower bound as 270. Upper bound, again, I'll use 1,000. Our mean is 266. And our standard deviation is that's lovely 6.531972647. And when I calculate that, I get 0.2701. So why is this probability so much smaller? Well, it all goes back to there's a lower spread. Your standard deviation is definitely lower. Went from 16 to 6.53, whatever. And so the lower spread means there's a lower probability. And we will do our last example. The height of young women follows the normal distribution. So here is the population distribution. With mean 64.5 inches and standard deviation 2.5 inches. So here is the mean and here is the standard deviation. Find the probability that a randomly selected young woman is taller than 66.5 inches. So we can use our normal CDF. The population distribution is normal. Mean is 64.5 inches. Standard deviation is 2.5 inches. So normal CDF. Lower bound is 66.5. Upper bound, I like 1,000. You can use 100. I mean, it's not going to change your answer. Our mean is 64.5. And our standard deviation is 2.5 because this is from the population. So that's why I'm not calculating a different standard deviation. And that gives us a probability of 0.2119. Right? Now let's look at our simple random sample. So let's look at our sampling distribution. Oops. And you can see the mean is still the same. The spread is definitely smaller, but we can use the normal CDF. because our population distribution is normal, which is so much nicer. We don't have to do any normal condition here. So find the probability that the mean height of a simple random sample of 10 young women exceeds that 66.5 inches. So our lower bound is 66.5, upper bound 1,000. Mean, again, it's the same as the population mean. And our standard deviation this time is going to be different. So let's calculate it out here somewhere. So our standard deviation of the sampling distribution is equal to standard deviation divided by the square root of our sample size. And I punched that into my calculator and I got 0.790569,415. Do my second vars, and I get a probability that is much smaller due to that smaller spread, and it is 0.0057. And those are our notes for 7.3a. Have a great day, stat students.